Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. This is our laboratory report for Experiment 7 Estimation of Heat Capacity and Entropy Generation. Like I said before, laboratory report by Group 2 guided by Dr Aizuddin Supee. So as usual, me myself, Mohamad Fakhrul Rasyid bin Abdullah, and we have Ahmad, Lukman, Aqil, we have Mohamad Hanis, and last but not least, Afina Ainna. Okay, so right now we're gonna go to the introduction. So we have heat capacity and also the entropy. So the heat capacity or thermal capacity is the amount of heat required to increase the temperature of a given mass of a substance by 1 unit without causing a phase change. And heat capacity is based on the sample's mass and size as shown in figure 1. As you guys can see, if the mass is small, the heat up easily, and if the large mass, it does not heat up easily. And the heat capacity of various substances will determine how much the temperature will rise. As for entropy, it is a measure of disorder or randomness in a system and to measure how much the energy is unavailable to do work. Entropy are shown in figure 2. Next, we're gonna go to the application of heat capacity and also entropy. First of all, example of heat capacity would be the different specific heat capacity of materials. In industry, for example, aluminium have a low specific heat capacity where it heats up and cools easily, making it ideal for use in car engines. So the car engines are shown in figure 4 that are made of aluminium. And secondly, the example of entropy in our daily life would be campfire. It is because the solid burns and become ash, smoke, and gases, which all spread energy outwards more easily than the solid fuel. Another example would be ice melting, salt and sugar dissolving in hot water, and also the boiling water. And figure 5 shows a campfire. Okay, so next will be the objectives and scopes for our experiment. Right now, I'm gonna go through the objectives. So the objectives will be to estimate the heat capacity and entropy generated for copper, aluminum, and also iron. Next, we're gonna go through the scopes. The scopes is the metal used in the experiment, like I said in the objective is copper, aluminium, and also iron. So we use corn oil as the medium to heat up the metals, and it is set up at 80 degrees Celsius maximum. And the temperature are also recorded at 10-second interval.
Now we are moving to the part of theory. So the first theory is about the heat capacity. So the heat capacity is the physical property of a material that defines the amount of heat energy required to rise the temperature of 1 kilogram of the material by 1 degree Celsius or 1 Kelvin. So below is the formula of the heat capacity, which is Q equals to mCp change of T. Q is the heat capacity, M is the mass, Cp is the specific heat of an object, and change of T is the change in the temperature. So in this experiment, we will be determine the heat capacity of each metal by measuring how much heat it transfers to the corn oil when it's cooled. So by knowing the Cp of the corn oil, we will be using to calculate the heat loss by the metal during the cooling. The second theory is about the first law of thermodynamics. So, what is the first law of thermodynamics? It is a state that energy cannot be created or destroyed, only transferred or converted from one form to another. So, this is the equation of the first law of thermodynamics, which is change of U equals to Q minus W. The change of U is the change in internal energy. Q is a being added or released to the system, while the W is the work done by or into the system. So in this experiment, we will be expect that the total heat lost by the Q metal will be equal to the heat gained by the corn oil, which is Q oil, by assuming there is no heat is lost to the surrounding, which is the Q metal minus Q oil equal to zero. Next, the theory is about the second law of the thermodynamics. So it is a state that the entropy of an isolated system always increases in any spontaneous process. Heat flow naturally from hot object to a cooler one, and this process generates entropy. Figure 6 show the illustrated how the heat flow from the hot object to the cold object. So the second law of thermodynamic will be using this formula, which is S gen equals to change of S metal plus change of S oil. So heat flow from the hot metal to the colder corn oil. So the entropy of the metal will be decreased as it lost heat, which is change of S metal less than zero. And the entropy of the corn oil will be increased as it gains heat, so the change of S oil will be greater than zero. So this reflect the irreversibility of heat transfer as energy is dissipated in the form of entropy. So the next theory is about the entropy. The entropy is a measure of a disorder or randomness in the system. It also quantify the dispersal of energy within a system. The metal at higher temperature has more concentrated thermal energy. When it transfers heat to the corn oil, this energy becomes more dispersed. So the formula for the entropy is the change of S equals to mCp ln times T2 over T1. The change of S is the change of entropy, M is the mass, Cp is the specific heat of an object, T2 is the final temperature, and T1 is the initial temperature. So in this experiment, the decrease in entropy of the metal, which is the negative change of S metal, is smaller in magnitude than the increase in entropy of the corn oil, which is positive change of S oil. So the ensuring is a net positive entropy change.
Assalamualaikum. My name is Afina Ainna binti Ahmad Razani, and I will continue our experiment for apparatus and the setup. So here are our apparatus. We have three different metals. The first one is the copper, aluminium, and also iron. And then we have the electronic balance, thermoplate, two beakers. We also use the medium using corn oil. We have the aluminium foil cap, the thermometers, stopwatch, and metal string. So the first one, the weight of the copper metal was recorded by using an electronic balance, and the data was recorded in the table 1. And then 100 millimeter of corn oil was poured into a first beaker, which then this beaker and the corn oil was heated on the thermoplate. Next, the copper metal was fully submerged into the 100 millimeter of corn oil by using the metal spring. And then the copper metal was heated in the corn oil bath until it reaches 80 degrees Celsius. So in this step, the thermometer was used to check the corn oil bath temperature as in the figure for the accuracy of the temperature. Next, while waiting for the corn oil bath to reach the 80 degrees Celsius, and then we filled the second bar with 100 millimeter of corn oil, and then the initial of the temperature was measured and recorded in the table 1. Once the temperature of the corn oil in the first beaker reaches 80 degrees Celsius, so the copper metal was immediately transferred into this second beaker using metal spring as in the figure. Next, the second beaker was immediately covered with an aluminium foil cap, and then the thermometer was inserted in the beaker by poking a small hole onto the foil cap. After that, the temperature of the corn oil in the second beaker was measured and recorded at 10-second intervals until it reaches a constant temperature, and all the data was recorded in the table 2. The corn oil was stirred throughout the process to ensure the accuracy of the temperature reading, and then the procedure was repeated by replacing the copper metal with different metals which are aluminum metal and also iron metal. Next up is about the data recorded. So all the data in the table 1, which is the mass and initial temperature of corn oil and metals, and the table 2, data of temperature con oil at 10-second interval was being completed. After these two tables completed, the specific heat capacity Cp for all the metals was calculated by using the formula delta Q equals to mCp delta T by using the formula of Q in equals to Q out, which is delta Q con oil equals to the delta Q metal respectively. And then after we have the Cp value of every metal, the entropy value was calculated by using the formula delta S uh, respectively of the metal equals to mCp ln T2 over T1. Okay, calculate this entropy value for all the metals calculated, and then we have the percentage error was also calculated by using the equation percentage error equals to V experimental minus V actual divided by V actual times 100, and the data was recorded in the table 3. Last but not least, a graph of specific heat capacity Cp versus the metals was plotted in the graph 1.
My name is Mohamad Hanis and I will explain about raw data and expected result. This is table 1, which are mass and initial temperature of corn oil and metals. So for the mass of corn oil is, and then we have table 2, which is the data of temperature corn oil at 10-second interval. So the table is start from 0 to, this is the continuity of table 2 from 90 second to 150 second. To get the equilibrium temperature of corn oil and metals, we need to have three consecutive readings. So we can see that for copper metal, the three consecutive reading is from 70 second to 90 second at 37 degrees Celsius. Aluminum metal is start from 90 second to 110 second at 34 degrees Celsius. And last but not least, iron metal. The three consecutive reading for iron metal is from 100 second to 120 second at 35 degrees Celsius. This is table 3, which is the data of temperature metals at 10-second interval from 0 to 80 degrees 80 second. And this is just the continuity of table 3 from 90 second to 100. And then we move to the calculation part for copper method. By using the data that we have record and get from the internet, we can find the specific heat capacity Cp for copper and total entropy. Using the formula Q metal minus Q oil equal to 0 that have explained in the methodology, and we can rearrange the equation to Q metal equal to Q oil, and also we know that Q equal to mCp delta T. It means delta T here is T2 minus T1. We just simply substitute the value into the equation, and then we can just solve it, and lastly we can find the Cp for copper is equal to 0.513 kilojoule over kg Kelvin. For the total entropy delta S, the formula that we need to use is delta S equal to mCp ln T2 over T1. So we need to find delta S for copper and the delta S for oil by just using the formula and substitute the value into the formula. After that, we can find the S generation by using the equation S gen equal to delta S metal plus delta S oil. So we can get the value as we can see in the slide. This is the calculation for aluminum metals with the same method and step. We can find the specific heat capacity but just change at the equilibrium temperature of corn oil and then the mass of the aluminum. Uh, Lastly, we can find the Cp of aluminum is 0.955 kilojoule over kilogram Kelvin. For the total entropy delta S, also using the same formula and same method, we can find the delta S for aluminum is negative 2.931 10 power of negative 3 kilojoule over Kelvin. For the delta S oil is 3.171 10 power of negative 3 kilojoule over Kelvin. And for the S gen, delta S aluminum plus delta S oil. Lastly, we can get the value is 2.402 10 power of negative 4 kilojoule Kelvin. Last but not least, we take a look at the calculation for iron metal. Same with before, just change in equilibrium temperature of corn oil or iron and mass of the iron. We can find the specific heat capacity Cp at 0.403 kilojoule over kilogram Kelvin. And then for total entropy delta S, by using the same formula again and same method, same way and the same step, we can get the delta S for iron is negative 3.511 10 power of negative 3 kilojoule Kelvin. And then delta S oil is 3.799 10 power of negative 3 kilojoule over Kelvin. And last but not least, S generation, we can get the value at 2.877 10 power of negative 4 kilojoule over Kelvin.
Okay, so right now we're gonna go to the discussion part. So we have the first part of the discussion will be the comparison of estimated heat capacity with the data from the experiment. Okay, we're gonna calculate the percentage error, which experimental value minus the actual over actual times 100%. As for copper, the theoretical value would be 0.377, whereas what we got from the experiment is 0.513. And the percentage error would be 36.07. And we have aluminium 0.921 for the theoretical value, and we have experimental value of 0.6955, and we have 3.58 percentage error. And last but not least is iron. We have 0.460 for the theoretical value, and the experimental value is 0.403, and we get 12.39 percentage error. Okay, so we're gonna go to the second part of our discussion. It will be a plot a bar chart of CP of metals. As you guys can see from the graph, we have three metals, which is copper, aluminum, and also iron. And the highest CP would be aluminum, followed by copper, and last but not least is iron. Okay, so right now we're gonna go to the third part of our discussion will be to discuss about the total entropy generated during the process. We know that the CP of aluminum from the experiment is 0.955, where followed by copper, where ACP is 0.513, and last but not least iron is 0.403. And we know that from the processes produce positive entropy values, where confirming their compliance with the second law of thermodynamics, which states that the entropy can only increase or remain constant. The presence of positive entropy in each case indicates that this process is irreversible, reflecting a natural progression toward greater disorder. And these varying levels of entropy underscore the distinct behavior of each material, with aluminum show the greatest disorder, followed by copper, and last is iron. So next, we're gonna go to the fourth part of our discussion about sources of error and method to minimize the error. So we have four sources of error and the way to minimize the error. First of all, the parallax error when reading the thermometer reading, and how to minimize this error is to make sure eyes are perpendicular with the scale of the thermometer. Second, sources of error would be the heat heats up slowly and not distributed evenly in the beaker. So we must stir the beaker throughout the experiment. And the third one is there is many heat loss to the surrounding. So we must wrap the beaker with aluminum foil and the fan are switched off. And last but not least, the thermometer is defective and we must make sure that thermometer is good to use. Okay, so right now we are still in the fourth part of our discussion, where the second question will be the justification on the importance of stirring the water in the container. Okay, so what is the justification? So the stirring the water in the container helps to evenly distribute the heat, ensuring a consistent temperature throughout the water. When the water is heated or comes into contact with other materials, such as metal, stirring eliminates temperature gradients, allowing for more effective heat transfer. This uniformly this uniformity is crucial for accurately measuring temperature and analyzing the heat transfer process. Additionally, stirring prevents localized overheating or cooling, which enhance the reliability and repeatability of the experiment. In summary, stirring the water is an important step to ensure accurate and effective experimental results. Okay, right now we are at the last question of fourth discussion where justification on the importance of transfer the quick hot metal quickly into the water. So we can minimizing the heat loss is one of the most critical reason for quickly transferring the hot metal into the water. Why? As soon as the metal is removed from the heat source, it begins to lose heat to the surrounding environment. This heat loss can significantly affect the experiment result, leading to inaccuracies in the temperature reading of both the metal and the water. A rapid transfer helps retain more of the metal's heat energy, ensuring that the recorded temperature in the second beaker is reflective on the metal's actual temperature at the time of immersion. By reducing the time the metal spends in the air, the experiment can more accurately capture the heat transfer dynamics between the metal and the water, ultimately resulting in more reliable measurements of the specific heat capacity. Next, I will pass to Afina for the safety procedures. Thank you.
Moving on to safety procedures, the first one is that we have to wear PPE such as lab coat, shoes, and wear heat-resistant gloves to prevent blister when handling a hot beaker. Next, ensure safety handling is done when transferring beaker on and off the hot plate to ensure no spilling happen, which can cause the machine to broken and injury to the students. The third one is if spill happens on the thermoplate, ensure to wear glove and use stick cloths to clean the spill to avoid blister from the hot thermoplate or ask for lab assistance help. Fourth, handle thermometer with caution to prevent breaking the thermometer that can cause the mercury in the thermometer to evaporate to the air, which is harm for us to inhale. Make sure to handle glass equipment with safety and cautious to ensure no accidents on beaker breaking that can cause cut to skin or bleeding.
In conclusion, this experiment demonstrates the determination of the specific heat capacity and entropy change of metals using corn oil as the heat transfer medium. The result was obtained by calculating the specific heat capacity, where aluminum has the highest heat capacity, which is 0.955 kJ over kilogram times Kelvin, followed by copper 0.513 and iron 0.403. Then table 4 shows the percentage error of each metal as well as the theoretical and experimental specific heat capacity. The entropy of the metal decreased as it cooled, while the corn oil's entropy increased, resulting in a net positive entropy generation, which is 2.402 times 10 to the power of negative 4 kilojoule over Kelvin for aluminium, 3.819 times 10 to the power of negative 4 for the copper, and 2.877 times 10 to the power of negative 4 for iron. The result highlight the differing thermal properties of metals and fluid, emphasizing the role of specific heat capacity in heat transfer and the irreversibility of natural process. This is our first slide of the reference, and this is our second slide of reference.